In this video, we will wrap up our look at alkanes and cycloalkanes, focusing briefly on physical and chemical properties. When we talk about physical properties, we're thinking about things like melting point, boiling point, and solubility. Well, if we compare the boiling point of methane, ethane, and propane, methane boils at about negative 160 degrees Celsius, ethane negative 89, and propane negative 42 degrees Celsius. So we know that because there is no dipole in these molecules, they are held together by induced dipole interactions, also known as London dispersion forces. And for dispersion forces, as the molecule gets bigger, we can think of it as the number of dispersion forces increases, and so the strength of the intermolecular forces increases. And as the strength of the intermolecular forces increases, the boiling point increases as well. Also keep in mind, if we look at the boiling points of the pentane isomers, so this one has a boiling point of 36 degrees Celsius, 28, and 9 degrees Celsius. So all of these have the same molecular weight. They're all C5H12, but now we have a difference in surface area. So this one is more spread out. There's going to be the most room for induced dipole interactions between one molecule of pentane and another molecule of pentane. Here, it's a little bit more compact, and here it's even more compact. So now we're talking about kind of a spherical shape. And so there's a lot less surface area, so less room for induced dipole interactions. So not a lot of contact between one molecule of 2,2-dimethylpropane and another molecule of the same. So for the same molecular weight and the same type of intermolecular forces, as the surface area increases, the boiling point will increase. And in terms of solubility, we can think about water solubility, not much. So these compounds are not going to be soluble in water because water does not want to give up really strong hydrogen bonding interactions with other molecules to settle for induced dipole interactions with these alkanes. They will be very soluble in nonpolar solvents, such as other alkanes, something like benzene or toluene, or other nonpolar solvents that we may use in lab. As we think about chemical properties, we're really talking about reactions, and alkanes are not going to undergo very many reactions. We can think about functional groups as where the chemistry happens. Well, alkanes are not functional groups, and that is kind of fitting because they're not going to undergo many types of reactions. Well, what about acid-base reactions? Well, if we have methane, this has a pKa of about 60. So that is an incredibly weak acid, and so this isn't really going to be undergoing acid-base reactions. Now the conjugate base, CH3-, this is a very, very, very strong base because methane itself is such a weak acid. We can use methane to approximate the pKa for other alkanes as well. So any alkane is going to have a pKa of close to 60. Well, what about combustion? Alkanes will undergo combustion. So if we have CH4, this will react with oxygen to form carbon dioxide and water. And we can come back to balance our equation. And so here we're going to have 2 waters and 2 molecules of oxygen. Now, combustion is a useful reaction to run our cars and get us to work in the morning, but combustion of alkanes is not a synthetically useful reaction. However, combustion can be useful if we use the heat of combustion to be able to compare stability of different compounds. So let's say we're looking at the 3 different isomers of pentane. They all have the same molecular formula, C5H12. And if we balance this equation, we need 5 molecules of CO2, 6 molecules of water, and then 8 molecules of oxygen. Now, Because these have the same molecular formula, we're talking about the exact same balanced equation. Now, in Gen Chem, you probably looked at ways to calculate the delta H, the heat of reaction. Well, in particular, we can use the delta H, specifically of combustion, and we can use this to give us information about our compounds. So these reactions are exothermic, and if we measure the heat of combustion in something called a bomb calorimeter, then we find that pentane has a delta H of negative 3535 kilojoules per mole. 2-methylbutane, it's negative 3528, and 2,2-dimethylpropane is negative 3514. Now, if we were to put this on an energy diagram, so here's energy increasing in this direction, and this axis would be the reaction progress. So if this represents the energy of pentane, then maybe this represents the CO2 plus water. And then this difference is 3535. Now I'm going to reuse this space, but using a different color. If we have this representing 2-methylbutane, now this difference is 3528. So it's a smaller distance. The red is a smaller distance than the black. And then finally, if we look at the third one, let's say this represents the energy of our third isomer, where this difference is 3514. So what do we do with this information? Because all three of these combustion reactions have the same ending point, by measuring the heat of combustion, we can figure out the starting point. And we can see that there is a difference in the starting energy of the different molecules. So this isomer is less stable than the other two. This isomer is more stable than the other two, and this guy is right in the middle. We don't need to know why there is this difference in stability, but I want you to understand this approach about using the heat of reaction to figure out the starting point, to figure out the relative energies, or the other way, the relative stabilities of different compounds. One of the other reactions that alkanes will undergo is a reaction with halogens in the presence of light and heat. And so in this case, if we have an alkane, so R can just be a CH3 group, or it could be a huge alkane, it is possible for this hydrogen to be replaced by a halogen. So if, for example, we have CH4, we can react it with chlorine in the presence of light and heat, and this will give us CH3Cl plus HCl as a byproduct. But with this reaction, it can also react further to replace another hydrogen and make more HCl. It can react further to replace another hydrogen to give CHCl3, and it can react even further to give us carbon tetrachloride at the end. We're going to talk about the details of this reaction in Chapter 6. You're not responsible for this reaction yet. For now, I just wanted you to be aware that there is one reaction of alkanes that can be synthetically useful, and we'll come back to this in Chapter 6.